Hey, how are you doing? Are you calculus students? Good, we have the right video then. This is part one of four. I'm going to have four videos that go with A10. There's four videos because there's lots of stuff, and if I try to do it all in one video, I'm bound to make a mistake. And it will nicely separate what we're doing. So this is called the definite integral. We don't even know what a definite integral is, but we are going to start by exploring the area under a curve. We're going to have the first video is just going to show us how we might use a calculus approach to find the area under that curve. We're going to do another video that is going to get more sophisticated, finding the area under that same curve. We're going to stop at that point and say, okay, what kind of intuitions are we getting from this? How are area and slope related? And that's an important thing that we're going to get to. And then finally, we'll give you the fundamental theorem of calculus. There is a little bit of hand waving here in that I'm not going to prove the fundamental theorem of calculus because it takes me 4 days to prove in class. So what we're going to do though is give you enough, just an example here where you can use your intuition to say, I see where, usually we know something before we prove it, right? We run into something and we have an idea that something is true and we need to test it in some way or prove it in some way. And I'm going to hopefully give you enough that you feel confident in making your conjecture that yes, that the fundamental theorem of calculus is true based on what I've shown you, and hopefully you won't require the proof. If you do, I think Katie Ross has it. Anyway, the area under definite integrals. Or in the area under definite integrals. The area under a curve. Let's start here. Let's find the area underneath the curve f of x equal to x from 0 to 5. And you're saying, Mr. Powers, that's a triangle. That's really easy. The area is 25 halves, right? Because it's 1/2 the base times the height. 25 halves. Okay, good. But we're going to examine it in a more sophisticated way so that we can try to find, how are we going to find the area in this region maybe? You know, this is not a nice shape and we don't know how to do that, so we're going to get there. Okay, to do this, I'm going to divide this area here into 5 equal intervals. Right, and this is 1, this is 2, 3, 4, 5. 5 equal intervals, each of 1 unit width, and I'm going to sketch some rectangles here. I'm sketching rectangles because I know how to find the area of rectangles. It's really easy. It's just the height times the width. The width of these each is 1, and we can find the height by putting the x value into the function. Right? Boom. This is f of 2, f of 3, f of 4, f of 5. So I can say then that the area under the curve from 0 to 5 is approximately f of 1, the height, times 1, plus f of 2, the height, times the width of 1, plus f of 3 times 1, plus f of 4 times 1, plus f of 5 times 1. And that's approximately the area. You notice that it's going to be too high, right? All these little pieces. So all those little pieces of area are in our sum, and so we are high by that much. So how could we make this better? More rectangles. Good idea. We can let the number of rectangles get really large. I will point out too that if the number of rectangles get really large, then the width of these intervals is getting really small too. That should make sense. Okay, so I'm going to introduce new notation called summation. And you've seen it before, maybe it looks a little intimidating, but the summation from I equals 1 to 5 of I, this is just saying, this is the Greek letter sigma, it just means add. So it means add i's. This is what it wants you to add, but it wants your i's to go 1, and then 2, and then 3, all the way to 5. So this is 1 plus 2 plus 3 plus 4 plus 5. if we did the summation from I equals 1 to 4 of I squared, we're adding I squareds, but we're letting I equal 1, 2, 3, 4, etc. So we have I squared is equal to 1 squared plus 2 squared plus 3 squared plus 4 squared. Okay, so it's just fancy notation. It saves you a lot of time. This one here, if I change this to n, and we have n, we're going to go 1 plus 2 plus 3 all the way to some number n. There's a closed form for that. This closed form means that if you're going to add up all those numbers, it equals n times n plus 1 over 2. So wherever you stop, that's what the sum's going to equal. I'm sure that's familiar to you. Okay? So, how is that going to help us over here? We are not going to do 5 intervals anymore. We are going to do n intervals. Okay? So we're going to split them into n intervals. We're going to come here. Boom. There's 1. There's 2. There's 3. There's 4. There's going to be n of them. And if there is n intervals, or n rectangles, they each have a width of 5 over n. Right? When we did 5 rectangles, the width was 5 over 5, or 1. So now we have n intervals of 5 over n. The first one here is just at 5 over n. That's the distance from 0 to this x value that we want to find the height of the rectangle. This one is 5n twice, so we're going to call this 5 times 2 over n. This one is 5 times 3 over n, so on and so forth, until the last one, which is 5 times n over n, right, or 5. Okay, so the area here then is approximately, I'm going to say approximately because we're using n rectangles, n being a finite number, is the summation from, oops, I'm not going to do that yet. We have f of 5 over n. This is how tall is this rectangle, then let's multiply it by 5n, the width. Then we're going to do plus f of 5 times 2 over n times 5 over n. And then we're going to do f of 5 times 3 over n times 5 over n. And finally, 5f plus f of 5 times n over n times 5 over n. Okay? So, each of these terms has a 5 over n, so I'm going to pull it out. The area is approximately 5 over n times I'm jumping ahead of myself here. F of 5 over n plus f of 5 times 2 over n plus f of 5 times 3. I'm doing some things here. F of 5 times 2 over n plus f of 5 times 3 over n plus plus f of 5 times n over n. And then I enclose my parentheses. Okay, so 5 over n's being multiplied by all of that. And now I'm just going to evoke this new summation notation. And I'm going to say that the area is approximately 5 over n times the summation from I equals 1 to n of f of 5I over n. Okay? So, if I was to write this out, now what we're going to do is we're just going to evaluate the function f at 5I over n. And the function is just f of x equal to x, so we have 5 over n times the summation from I equals 1 to n of 5I over n. Okay? And if you were to put this out, you would have 5 over n plus 5 times 2 over n plus 5 times 3 over n. I'm going to write that actually. And you notice then that each one of these has a 5n term, and so we can pull that out as well. So I'm going to, right, you see that? I could write a summation right here. After I take these 5n's out again. So I have 25 over n squared times the summation from I equals 1 to n of, 1 plus 2 plus 3 plus 4, or I. Right, so, I don't like the summation there. Okay, you see what I've done there? We already have this 5n here. I rewrote this summation and pulled this 5n out again. And so we have that the area is approximately 25 over n squared times the summation from I equals 1 to n of I. But remember, I just gave you a closed form for this. It is 25 over n squared times n times n times n plus 1 over 2. And so I can rewrite that as 25 n squared plus 25n over 2n squared, which I can further decompose fractions as 25n squared over 2n squared plus 25n over 2n squared, which is going to reduce to 25 over 2n. All right, and so now I can say that the area under the curve is approximately 25, and notice our n squareds cancel here, 25 halves plus 25 over 2n. Okay, and that is the area under the curve for n rectangles. But now we can say that the area is equal to the limit as n goes to infinity of 25 halves plus 25 over 2n. And lo and behold, what do we get? This term goes to 0. Wow. Huh? So, that's that. That's how we use summation to find the exact area under this curve from 0 to 5. When I come back on the next video, I'm going to do it really generally, and I'm going to put a b there. Okay? I'll see you then.